afternoon, everyone. Before you run off to fill your bellies, I'm going to invite you to take a short journey with me. So imagine you have collected some data set that can be represented in a number of features, but here's just one two-dimensional projection. And imagine that you sweat over this data in order to collect labels and then build a machine learning model. This is very hard work, as I think many of you in this audience know, right? And then you have your machine learning model and you think, ha, nature, here I come in order to unravel thy mysteries. And nature spits in your face and laughs. Classify this, astronomer. Because anytime we build machine learning models, we have to do so with data for which we can actually get labels. And those labels come from the highest signal to noise data we have, right? They come from spectra, they come from sources that you look at with your eyes, they come from simulations, okay? But these labels do not perfectly represent what actually is out there in nature. And what this means is that once you try to apply your models, you have to deal with the fact that many of the sources you may be applying your model to are out of distribution. And this is a real pain. It's a real risk if you want to go get follow-up time. In particular, TACs tend to be conservative. So if you say, I've built this model and now I want to go get follow-up, right? This particular risk is really bad news. So I think I've come up with one possible tiny solution, not the generic solution to this problem. And that is to build and deploy your models on small telescopes that are not particularly valuable in terms of the time that you use, okay? And in particular, I'm going to talk today about the Zwicky Transient Facility. We've heard a lot about ZTF. I won't do a major overview, but I just want to emphasize that the real power of ZTF is the huge field of view, 47 square degrees. You could basically get all of Orion in just 3 pointings. Within ZTF, one of the things we've been running for the last several years is the Bright Transient Survey. Christopher Fremling has a poster on this, so you can learn more about that there. But what I want you to know is that essentially the goal of this project is to obtain a spectrum of every transient in ZTF that gets brighter than 18.5. And this has become a huge community resource, and it's become very valuable. And in fact, many discoveries that have been mentioned throughout this conference have been supported by the fact that we've been collecting these spectra as part of BTS. Now, what you may not realize as part of what we're doing for the Bright Transient Survey is actually going in and deciding what are the sources that are real, what are the sources that are not real, and allocating spectroscopic resources in order to follow all of these up, right? What that looks like is every day some person comes into the office and has to look at hundreds of candidates deciding which are the real supernovae that deserve spectra, okay? One of the unknown costs for the Bright Transient Survey is we've had to buy a lot of buckets, which we use to collect the tears of the people that do this every day. Okay, so after several years, this led me to think, surely we do not have to be doing this anymore. We must be able to find some way to automate this. And so here enter BTS Bot. All right, and we're trying to essentially answer the question, can we use machine learning to find bright supernovae? And this is a little bit of a more complex problem than just saying, is this thing a supernova? And there are many tools out there that will do that, right? The specific question we want to answer is this a supernova that will eventually become brighter than 18.5 and enter the spectroscopic sample for this project? Okay. This is work that's been largely led by Nabil Rahimtullah, who's a graduate student working in my group. And I'm going to walk through basically how we got to the solution to this problem. I hate staring at diagrams like these, but I know some people love them. So what I'll just quickly say is that the inputs for the model we built include the cutout images from the ZTF alert packets, plus a little bit of additional information. So this is a multimodal model. It's not solely built on the images. It's not solely built on features that are extracted from the data. We combine the two. And in the short upshot, what we were able to find is that, yes, in fact, we can build a machine learning model that can solve this problem. And it can even do so often before the supernova has actually reached that brightness threshold of 18.5 magnitudes that I mentioned a moment ago. I just wanted to give you a sense of the kinds of things that we find. So even the sources that just barely get above this, arbitrary threshold of 18.5, we are able to classify those. We do have plenty of false positives. Again, I want to give you a sense of that. So in the center, panel here, right? If we have something that just barely misses the threshold, the model will often call that a bright supernova, but strictly speaking, by our definition, it is not. And we can, on occasion, also have bright CV flares. That's what you see on the far right column here that will cause a false positive in the model. But overall, the performance is quite strong. The completeness is greater than 99% for these bright transients, and the purity is about 93% in our test sets as we were training this model. So as we deploy new spectroscopic resources, we very rarely are actually taking spectra of something that is not a bright supernova. And in many cases, if we do miss a bright supernova, it's one thing like in this middle panel, a supernova that's 18.6, right? Just barely below the threshold. Okay, so now I want to tell you a story about a very specific supernova, and perhaps not a rare gem, but one that I still think is relevant for this conference. So in late October, ZTF found a new transient. BTS bot took a look at this thing and said, I believe this to be a bright supernova. It then triggered spectroscopic follow-up observations with the P60 SEDM instrument, right? A spectrum was obtained the next night. That spectrum was classified by another machine learning model, which was developed by Christopher Fremling, called Supernova 1A score, and classified to be a type 1A supernova. And this was then announced to the transient name server. This was the first ever time, I believe, in history that everything, the initial observation, the identification of a possible transient candidate, the request for follow-up observations, the collection of a spectrum, the classification of that spectrum, and then the announcement of this particular supernova, all of this happened automatically. Okay? It's quite possible this will be one of the most important discoveries that ever comes out of my group, and all of it happened while we were asleep. Okay. This is now something that's running in production. So another thing that can be quite scary when you build a machine learning model, this is not just cross-validation. This is actually every single night looking at new candidates. More than 100 million alerts have passed through BTS bot at this point. 500 spectra have been requested, and we're up to almost, not quite, but almost 100 completely automated, the machines do all of it classifications, no human in the loop. So I think this is quite exciting. And I think this is a mode that we all have to be thinking about how we can shift our workflows to this as we get into the Rubin era. Because again, unless you want to buy even bigger buckets than the ones we did to collect the tiers of your students and postdocs, there is no way that we're going to be able to look at everything that's coming out of the Rubin LSST stream. Okay? If you don't believe me that this is a big deal, I do just also want to say that this is something that has inspired poetry. BTS bot, the silent sentinel of the skies, with algorithms as its guide, seeks out the universe secrets one supernova at a time. All right, I don't think this was actually written by a human, but whatever. It's pretty funny that someone wrote a poem about a machine learning model we built. In my last couple minutes, I want to transition to tell you about a different project, one that's coming online later this year, called the LaCie Southern Sky Survey, or LS4. So just very briefly, I'm going to introduce this project. So LS4 is a new project being run on a shoestring budget. And the way we're able to pull this off is we're reusing a whole bunch of existing facilities. So this is a new time domain survey that's going to run on the 1 meter Schmidt telescope. We're using the Quest camera. So this is an existing camera, but we're going to retrofit it so that we can fully fill out the 20 square degree field of view. We're doing this with detectors that were built and fabricated for DE-CAM. The yields when Fermilab was making these CCDs were actually much higher than expected. And there was a lot of science grade CCDs that literally were sitting in a closet at Fermilab for over a decade. And fortunately, we are able to use those now. And that's how we're able to build out this 20 square degree field of view. All in all, we have a 268 megapixel camera with 1 arcsecond pixels. And in our planned exposure times of about 45 seconds, we'll get down to 21st magnitude in G band and 20th magnitude in Z band. There's no filter wheel. There's no space for this within the camera. So we have this, what I'm calling super novel, but really out of necessity, a multi-filter passband. So we're going to be covering the different quadrants with different filters on the detector, and then we'll dither to get colors. Half the focal plane will be covered in I-band, and with another quarter being G-band and the last quarter being Z-band. So we're leveraging the fact that the LBNL CCDs are very red sensitive to make sure that we're capturing mostly red optical light with this survey. Most of the science that will be done by LS4 is going to be done via a public survey. So 90% of the open shutter time will be dedicated for this public survey, which will primarily be a rolling extragalactic survey. We'll use dithering to get G and I one night, and then the following night we'll come back and get I and Z. So you'll always be getting I band observations and then colors as we go. This is going to be a few thousand square degrees on a rolling cadence. There's also going to be a focused galactic plane survey, and there's another poster by Maisie that's right over here. And you can learn about the microlensing survey that we'll be doing in the galactic plane as well. All alerts from any new transient candidates that are found by LS4 will be made immediately available to the public. This is going to enable a lot of exciting science. I'm just going to roll through this really quickly because I'm getting short on time. Our red sensitivity will make us particularly good at finding lensed supernovae because we have a G band. We'll also be good at picking out tidal disruption events based on their blue colors and long time scales. Also sensitive to fast blue optical transients, infant supernovae, flash spectroscopy. We'll do a lot of supernovae so we can measure peculiar velocities. And I'm particularly excited to go after your favorite theorist's favorite idea. Hopefully it'll be there within the data. As I said, this is coming later this year. So here's a picture of the fully assembled focal plane. The camera's being built at Yale right now. Hopefully, this is maybe a mildly too optimistic, but we'll be shipping the camera down to Chile next month, getting it installed on the Schmidt the following month, and commissioning will then start in the Chilean winter. Survey begins hopefully end-ish of the Chilean winter, and very obviously in December of this year, we're going to find a binary neutron star counterpart from LIGO. That's why we're in such a big rush right now. But I think the big thing, circling back to my message from this talk, is that this is going to be going online about a year before Rubin LSST begins. And the reason why this is particularly exciting, I think for what should be exciting for many of you in this room, is that we have been using ZTF as a test bed. We're building machine learning models on ZTF, but what we say in our proposals or when we write grants is that we're building these models so that we can eventually apply them to Rubin. And that leaves out a critical step, which is that we have to understand how we can perform transfer learning on these things. We don't want to be doing that on the fly. We want to learn those lessons in advance, and LS4 is the perfect opportunity for that. So that's one of the reasons why I'm particularly excited about LS4, and I argue that those of you that are building models for ZTF right now, you should also be excited for LS4 because this gives you a stepping ground before we get to Rubin. All right, so in conclusion, astronomy is a story, machine learning and astronomy is a story about out of distribution data sets and TACs that really hate you. That's what I've concluded in my 10 years of working on machine learning. So I think the way to get around this is to build models on smaller aperture facilities where it's really quite easy, right? If I build a model and I destroy what happens with ZTF for one night, no one cares. If I build a model and I destroy what happens on Keck for one night, that's 2 grad students that I could have had in my group instead, right? So I think finding low cost, low risk places to deploy your models and make sure they work is a wonderful idea. BTS Bot is this really cool robot that runs on streaming data and is now making discoveries, full discoveries, not here's a thing and then people have to look at it, but actual full discoveries in our sleep. And I think LS4, which is coming soon, is going to be a wonderful test bed for all of us to figure out how we can transfer the models that we've built for ZTF to work in the next step, which will be once Rubin LSST turns on. Thank you, and I'll happily take your questions.